So the last key thing to helping us graph things using calculus is something called an inflection point, and that's where your graph changes concavity. So if you took something like an x cubed graph like this, the inflection point is right here, because on this side it's concave down, on this side it's concave up. So that can help us graph things because we can use our first derivative to help us find out where our maximums and minimums are, and now we can use our second derivative to find out where it changes from being concave up and concave down. So every time the graph lies above its tangents, in other words, what I mean by that is if I draw tangents on here, can you see that the graph is always above those tangents where they're blue? And if we make the concave down part red, here the graph is always below my tangent lines. That makes something concave down. But I think the happy face and sad face is the easy way to remember what concave up and concave down mean. So we will do happy in blue, not so happy in red, and just color code this. I'm going to use blue crayon instead of just blue. Concave up. Can you see from here to here? It's concave up. And then from here to here, it's concave up. From here to here, it's concave up. And then concave down would be this section and that section. Make some happy and sad faces. There we go. So at those points P, Q, and R on this last graph, they're all points where it changed from blue to red. And so those are called inflection points. Anytime your graph changes concavity, it finds inflection points. Now, we use the second derivative to test for concavity. Very much like we did with first derivative. Remember our first derivative, we found out where it's equal to 0 and then could find out if a graph was increasing and decreasing. We're going to do the same thing with the second derivative, the same kind of style, find out where it's positive and negative, and it will tell us where something is concave up or concave down. Now, all the second derivative is the first derivative of the first derivative. Does that make sense? If you do the derivative of the derivative, you get the second derivative. So if a derivative is a rate of change, and you're doing the derivative of the derivative, what we see here, in this case, in the two examples above, the slopes of the tangents are increasing. Can you see that I'm going from 0.24 to 1.07 to 4.05? And here I have a negative 1.4, and then a 0, and then a 1.63. If my slopes are increasing, that will mean my second derivative is going to be positive. Because if my first derivative is increasing, right? Let's think back to our first derivative test. Our first derivative test, we found critical points, critical 1, critical 2. And if it was positive, it told us that things were increasing. If it was negative, it told us that things were decreasing, right? And then if it's positive, it would be increasing again. That is just an example. That's what our first derivative did. So now, if we were doing the derivative of the derivative, can you see in both of these situations that our derivative, our first derivative, is increasing? If our first derivative was increasing before a critical point, that's going to tell us that our original function is concave up. Yes? So the derivative of the derivative. So if I'm just looking at my first derivative, so here's the black is my original function. On that original function, I've got a bunch of tangents, and I can see that these tangents are increasing. They're getting steeper. Here, they're still increasing. See, I'm at a negative number, then I get to 0, then I get to a positive number. If I did another one, it would be even steeper than the last one. And any time that your derivatives are increasing, that'll mean that your original function had to have been concave up. Similarly, if our derivatives were decreasing, so the curve is my original function, and I've drawn a bunch of derivatives from left to right. I go from 10 to 1.4 to 0.29. Those values are going down. What does that make the curve of my graph? It makes my curve concave down. Yes? Well, the second derivative is looking at the change of the first derivative. So my second derivative is telling, when I look at my first derivatives, and I see that my first derivatives are decreasing, that would mean, right? If I'm saying my first, not my fist, they're my first derivatives are decreasing, what does that tell me about my derivative of my derivative? It had to have been negative. So my second derivative has to be negative. Okay? Well, it is, but then if you work all the way back, what does that mean about our original function? It makes our original function concave down. It is the same thing if I'm just going from my derivative to my second derivative, it's the same as we did before. But now if I compare those results to what happens in my original function is concave down. Now, if my first derivative is negative, it's just telling my function is decreasing. I can make a decreasing function concave down, or I can make a decreasing function concave up, right? But if I look at this one that's decreasing, so this one, if I look at my slopes, here I've got negative, looks like negative 1/3, and this one looks like maybe a slope of negative 2, and this one looks like negative 5. My slopes are decreasing. And so my second derivative is negative, and it's concave down. But if I look at this decreasing function, and I look at my slopes, here I've got negative 11, this one maybe is negative 1, and this one is negative 1/3. My slopes there are actually increasing. My original function's still decreasing, but my first derivative is increasing, and that's why the curve is concave up. Now, this is the reasoning behind why it's happening. What we're going to end up doing with this is rather simple. So, all we're going to do is use our second derivative to test for concavity. If we find out that our second derivative is bigger than 0, it'll always be concave up. And if our second derivative is less than 0, it'll always be concave down. If it changes from concave up to concave down, and it's equal to 0 in between, then we have an inflection point. So, to show that a point is a point of inflection, you have to show two things. Number one, you have to show that your second derivative, so for inflection point, number one, you have to show that your second derivative is equal to 0. And then part 2, and I'm going to go 2a or 2b. You have to show one of these two. 2a is probably the easiest one. Show that it changes concavity. And you will do this by making a number line, put your point where the second derivative is equal to 0, and if it goes from concave up to concave down, then you know at point C it had to be an inflection point. Because it's possible to have a second derivative equal 0 but not change concavity. Or you can show that your first derivative either stays negative or stays positive at that point. If it does not change sign at that point, then you know that it's an inflection point as well. Because the times where the second derivative is equal to 0 and it's not an inflection point are usually where it's a maximum or a minimum. I find a lot of people like this way to show an inflection point easier than showing that the first derivative doesn't change sign. So what does that mean for us? How do we show that something has an inflection point? Well, we would have our first derivative then we would find our second derivative. We would set that equal to 0 and factor to solve. We have two critical points for our second derivative. We can draw our number line and put 0 and 2 on there. And then anytime you're checking concavity, you're going to plug things into your second derivative. So on my number line with my second derivative, I plug into my second derivative. For my number line with my first derivative, I'd plug into my first derivative. So when we put this all together, and I left some space so we could kind of put this all together in the end, this is what it would look like. But for our second derivative, if I plug in something less than 0, like a -5, can you see that this is negative? And this factor is negative. A negative times a negative is positive. You can make it like a Cyclops happy face. That's going to be concave up. If I try something between 0 and 2, like 1, this now is positive, this one's still negative. This section will be concave down. And finally, something larger than 2, both of these will be positive, making this section positive. So now that we've done this, we can write our statement to show that it has a point of inflection. Since, first thing we need to show, f double prime at 2 equals 0, and 2 f of x changes from concave down right before x equals 2 to concave up after x equals 2. So we have to show those two reasons. That's why I numbered them. One, we have to show that the second derivative is equal to 0. And two, we show that it changes concavity, that it changes from concave down to concave up. We know that 2 comma, if I want to find out the actual point, I'd plug that back into my original equation, 16 minus 32, 2 comma negative 16, is an inflection point. We also know that at 0, it changes concavity, so 0 is going to be another inflection point. Can I move up? Yes? Almost? The definition of an inflection point is where the graph changes from concave up to concave down. And if we have those points, it's actually going to let us draw it easier. So I'll show you all of that. If we were asked to graph this completely with all stationary points, all inflection points, well, you've done your first derivative. You could set your first derivative equal to 0, factor out a common factor of 4x squared, and you get x equals 0 and x equals 3. Now, if we put 0 and 3 on our number line here, and we plug things into our first derivative, what does that tell us? That tells us where our graph was increasing and decreasing. So if I plug in something less than 0, like a negative 5, well, this is always going to be positive because it's an x squared. Negative 5 would make this negative, meaning this section's negative. Our original function was decreasing. If I plug in a value between 0 and 3, like 2, well, this is still positive. Plugging in 2 into the second bracket still gives us a negative here. This is still decreasing. And finally, after x equals 3, if I plugged in 5, they both are positive, so now our function is increasing. What does that tell us about 0 and 3? It tells us that 0, 0 is a stationary point of inflection, and 3 comma 81 minus, what is 27 times 4, 108? 81 minus 108, negative 27. That makes sense. That is a local min. So if you're wondering, how do all of these points help us graph? Well, with those two sign diagrams with inflection points, and here, I'm going to just draw my graph in this space right here. Okay, I'm going to need to label 3, negative 27, 2, negative 16, and 0, 0. So as far as my scales go, I'm going to make this 3, negative 27. 2, negative 16 would be about there. 0, 0, well, that one's pretty good. That'll be there. What do I know about this graph? It's got to be concave up, concave down, concave up. And I find it's actually easy to start from the point when graphing. So this side of 0, it's got to be concave up, and my function has to be decreasing. Wow, did it just go down on me there? There we go. Does that fit? And then between 0 and 2, it's got to be concave down, still decreasing. And then after 2, it's concave up. 3 is a minimum, so I need to just finish drawing it. Now, starting from the points and doing the concavity, see how nice our inflection point, the bend, ended up being in our graph? It naturally bent perfectly to change our inflection there. And we have an inflection point here, so it changed from concave down to concave up. The only other point that you would end up labeling on here would probably be this one. Where's that point going to be? Something comma 0. Well, that's an x-intercept. How do I find an x-intercept? Set my original equation equal to 0. If you factor out an x cubed, you'd have 4 comma 0. Now, we did more in that question than we needed to. The question only asked to show that it has a point of inflection. So we needed to do this, our first derivative, to find this, and then this section right here with the concave up and concave down, and then the reasoning is all we needed to do. But I wanted to show you how you could combine the first part and the second part together to graph it. Think you're ready to try one completely? So, here it says classify all stationary points and points of inflection. So you'll leave yourself space. You're going to find the first derivative, do your sign diagram with your first derivative to show where things are increasing and decreasing, and then you'll be able to label stationary points, maxes, mins, or stationary points of inflection. Then you're going to do your second derivative. And with your second derivative, you're going to do that sign diagram to find out where things are concave up or concave down, and then you're going to be able to label your inflection points. When you have both of those, you'll graph it completely. Other points, if you can find them easily, that are nice to put on your graph, are x-intercepts and y-intercepts. So, as far as figuring this out, we've got our first derivative. We take our derivative. If you didn't factor out that 3, it's not wrong, but it makes life a lot easier if you can take out a common factor, because then factoring the x squared minus 2x minus 3 is easier. Again, we find out increasing, decreasing, increasing, so that means that negative 1, 6 and 3 comma negative 26 are local max and local min respectively. Again, to find out where it's increasing and decreasing, you plug into your derivative. But then to find your actual points you always find by plugging the x value into your original equation. So once you've done your first derivative to find stationary points, you could do your second derivative, and you find out that there's an inflection point at 1 comma negative 10. And then we get the graph that we saw before. So I'll leave that up for a bit, and if you got that already, you can start the next one. So we'll scroll up. So we've got our first derivative, factor things out, do our number line to find out where things are increasing and decreasing. And with that, we get negative 1 is a local min, 0, 0 is a local max, and 1, negative 1 is another local min. Doing our second derivative right here, it just has an x squared. You could factor things, or you could just get the x squared by itself. When you square root, you have to remember plus or minus. So those are our intervals to find out where things are concave up and concave down. A little fun mental math finding those points. And you get negative 5/9 and 5/9. So I'll leave this, should I leave it like this for a bit, and then I'll scroll it down to the bottom after?